In the linked video, we have already explained form tolerances in detail. This focused exclusively on tolerating the form of geometric features such as straightness, flatness, roundness, cylindricity, profile of a line, and profile of a surface. In this video, we will take a closer look at positional tolerances, which can be divided into orientation tolerances, location tolerances, and runout tolerances. In the following, the orientation tolerance of angularity will be examined in more detail, which also includes the special cases of perpendicularity and parallelism. Basically, positional tolerances always have a so-called reference, also called a datum, because a position can only be meaningfully defined in relation to another geometric feature, unlike form tolerances. To illustrate this, the drawing depicts a part with an inclined surface. The slope is theoretically at an exact angle of 20 degrees. It should be noted that theoretically exact dimensions, so-called TED dimensions, are enclosed in a rectangular box. Unlike a nominal dimension, a theoretically exact dimension has no dimensional tolerances. In this case, no dimensional tolerance applies to the angle in terms of a plus-minus value, since the angle is not to be tolerated by a dimensional tolerance but rather by a geometric tolerance using the orientation tolerance of angularity. To illustrate this, the first box of the feature control frame contains the symbol for angularity, followed by the tolerance value in the second box. We will soon see how this value is to be interpreted. Next comes the reference box, since it is always necessary to specify the geometric feature to which the 20 degrees apply. In our case, the 20 degrees are to be defined relative to the underside of the part. Therefore, we place the datum triangle with the datum letter A on this surface and specify this datum accordingly in the reference box of the feature control frame. The tolerance zone now consists of two planes inclined to the theoretically exact angle of 20 degrees to a perfectly flat reference surface and spaced apart by our tolerance value of 0.05 millimeters. The part rests on this reference surface, also called the datum simulator, with its datum surface A. Every point on the tolerated surface must lie within the cuboid-shaped tolerance zone defined by these two planes. It is important to note that the tolerance zone for orientation can be shifted arbitrarily. Only the orientation of the planes at 20 degrees to the horizontal and their distance of 0.05 millimeters from each other must be maintained. Angularity as a positional tolerance ultimately includes two special cases. Basically, angularity can also be applied to a surface that is supposed to be perpendicular to another surface. In this case, the angle is 90 degrees. Since such right angles are not explicitly specified with an angle in drawings but are instead implied by the drawing itself, the tolerance for such perpendicularity is given its own tolerance symbol in the form of the perpendicularity symbol. However, the same procedure for creating the tolerance zone applies to perpendicularity as it does for angularity. The cuboid-shaped tolerance zone is formed by two parallel planes that are perpendicular to the theoretically perfectly flat reference surface, also called our datum simulator, and whose distance corresponds to the tolerance value. The tolerated geometric feature, in our case the side surface, must therefore lie entirely within these two planes. Another special case of angularity arises when the angular value is 0 degrees. This allows parallelism to be defined between two geometric features. In our case, this ensures that the top surface of the part lies parallel to the underside within the given tolerance. This type of positional tolerance also uses its own tolerance symbol in the form of two parallel lines. The tolerance zone is formed here in the same way as for angularity. That is, two parallel planes spaced apart by the tolerance value define the cuboid-shaped tolerance zone within which the tolerated geometric feature must lie. These planes are exactly parallel to the datum simulator, and the part rests on this surface with its underside defined as the datum. Angularity in general, and perpendicularity or parallelism in particular, can be applied not only to actual geometric features but also to derived geometric features. For more on the terms actual and derived geometric features, see the video on form tolerances. Let us consider the illustrated example of a part with an inclined hole. The center line of the hole runs at the theoretically exact angle of 40 degrees to the underside of the part, which is defined as datum A. To apply a tolerance to the orientation of this center line, we use the characteristic of angularity. Since in this case we are tolerating the center line of the hole as a derived geometric feature, we place the leader line in direct alignment with the dimension line of the hole diameter. This clearly indicates that we are not applying the positional tolerance to the inner surface of the hole, but rather to the derived geometric feature, namely the center line. In this case, the diameter value of the hole may also be placed above the feature control frame. When tolerancing the centerline of a hole, it is generally not appropriate to define the tolerance zone using two parallel planes. A cylindrical tolerance zone is much better suited for this purpose. To clearly indicate that such a cylindrical tolerance zone is to apply, the diameter symbol is placed in front of the tolerance value in the feature control frame. The centerline of the hole must now lie within a cylinder whose diameter corresponds to the tolerance value of 0.05 mm, and whose axis forms an angle of 40 degrees with a datum simulator or reference surface on which the part rests with its datum surface A. One might assume that specifying datum A clearly defines the position of the tolerance cylinder relative to the part. However, this is not the case, so a second datum is required if necessary for the function of the part. Let us consider the yellow-marked plane in which the axis of the tolerance cylinder lies. This plane ultimately corresponds to the drawing plane in which the geometry was specified and toleranced. One might assume that this plane, and thus the axis of the tolerance cylinder, is clearly defined relative to the part. However, this would only be the case if the part were manufactured exactly according to the ideal geometry shown in the drawing. Let us therefore consider two additional datum simulators B and C, which are both perpendicular to each other and each perpendicular to the datum simulator A. These reference surfaces ultimately form a right-angled coordinate system and define the position of our ideal part geometry. That means the top and bottom surfaces are parallel to datum simulator A, the side surfaces are parallel to datum simulator B, and the front and rear surfaces are parallel to datum simulator C. In reality, however, the surfaces of our part are neither flat nor perpendicular to each other. The animation illustrates an exaggerated example of a possible actual part geometry. It now makes a difference whether we align the left side surface of the part to datum simulator B or the rear surface to datum simulator C. If the part is aligned using the side surface on datum simulator B, then the axis of the tolerance cylinder is positioned relative to the part as shown. If, on the other hand, the part is aligned using the rear surface on datum simulator C, the position of the plane in which the axis of the tolerance cylinder lies will be different relative to the part. It is important to note that the plane in which the cylinder axis lies is always parallel to the theoretical drawing plane, that is, parallel to datum simulator C and perpendicular to datum simulator B. However, due to the non-ideal geometry of the part, its orientation relative to this plane changes, and this results in a slightly different position of the tolerance cylinder relative to the part in each case. If the function of the part requires it, an additional datum must therefore be specified in order to define the plane in which the axis of the tolerance cylinder must lie. In our case, this second datum B shall be the rear surface of the part. We therefore extend the feature control frame by adding another datum reference field with the corresponding datum letter B. We will later see that the order in which the datums are listed in the feature control frame also affects the orientation and position of the tolerance zone. Now we have clearly defined the position of the tolerance zone relative to our part. On the one hand, the axis of the tolerance cylinder must run at an exact theoretical angle of 40 degrees to the underside of the part, datum A, and on the other hand, the cylinder axis must lie in a plane parallel to the rear surface of the part, datum B. The tolerance cylinder itself has a diameter of 0.05 mm, within which the centerline of the hole must now be located. The dashed leader line of datum B and the open reference point indicate that the non-visible rear surface of the part is being referenced as the datum. Note that angularity as a positional tolerance always includes the form tolerance of flatness or straightness. Because the tolerance zone is defined by two parallel planes or by a tolerance cylinder, the flatness or straightness of a toleranced feature cannot deviate more than what is permitted by the angularity tolerance. In other words, the positional tolerance further restricts the form tolerance by controlling the position. The positional tolerance is therefore a stricter criterion than a pure form tolerance, which only controls the shape but not the orientation of a geometric feature. So note, all positional tolerances always include a certain form tolerance as well. In the following, we will take a closer look at the location tolerances, which can be used to control position, concentricity, coaxiality, and symmetry. To begin with, let us examine the tolerancing of position in more detail. The example shows a cuboid-shaped part with a hole. The position of the centerline of the hole is to be toleranced with respect to location. However, first, the location will be toleranced in the conventional way using dimensional tolerances, in order to better understand the difference compared to a positional tolerance. For example, we select a tolerance of plus or minus 0.05 mm for both dimensions. This results in a tolerance zone of 0.1 mm in both the horizontal and vertical directions. The center line of the hole must now lie within the resulting rectangular or cuboid-shaped tolerance zone. A disadvantage of such a tolerancing method is the rectangular tolerance zone, because the position of the center line may deviate less from a theoretical exact position in the horizontal and vertical directions than in the diagonal direction. Another disadvantage is that the specified dimensions of 68 and 114 mm do not have a clear reference. This is because, in reality, the part surfaces are neither perfectly flat nor exactly perpendicular or parallel to each other. For example, the specified dimension of 114 mm on the left side of the part does not have a clear reference point from which the measurement should be taken and maintained. Depending on the point from which it is measured, different dimensions result. And how does one even know how to align a skewed part to obtain the specified horizontal dimensions? The horizontal position could, for example, be defined by aligning the part on its left side against a perfectly flat reference surface. However, it is also conceivable that the top side of the part serves as the reference surface for the correct alignment of the part. This would then yield different dimensions. Aligning the part on the right side or the underside would also lead to different measurements. In conventional dimensional tolerancing, there is therefore no clearly defined position of the part that serves as the basis for meeting the dimensions, leaving room for different interpretations. To avoid these problems when tolerancing the position of the whole centerline and to ensure clarity, the position tolerance can be used. This type of location tolerance is symbolized by a cross with a circle at its center, resembling a crosshair. Since in our case the position of the whole centerline is being toleranced as a derived feature, the leader line of the feature control frame is again placed as a direct extension of the dimension line of the hole diameter. Since in our case a cylindrical tolerance zone is to apply, the position tolerance value is preceded by a diameter symbol. The center line of the hole must now lie within a tolerance cylinder with a diameter of 0.1 mm, where the axis of the tolerance cylinder must be located at the theoretically exact position defined by the dimensions given in the rectangular boxes. Note that no dimensional tolerances apply to this theoretically exact position. We have now avoided the first mentioned problem of the rectangular or cuboid-shaped tolerance zone and replaced it with a cylindrical tolerance zone. Now the second problem of correctly aligning the part must be solved in order to determine the theoretically exact position of the tolerance zone. To clearly define the orientation of the part in space, a total of 3 datums are required, one for each spatial direction. The first datum is referred to as the primary datum and is identified in our case by the letter A. It refers to the red-marked bottom surface of the part. This primary datum is listed first in the datum reference box. The secondary datum B is the left side of the part. It is specified in an additional datum reference box in the feature control frame. The final datum C, the tertiary datum, is the rear side of the part. It appears in the last datum reference box. It is important to note that it is not the alphabetical order that determines which datum is primary, secondary, or tertiary, but rather the order in which the datums are listed within the feature control frame. The first datum listed is always the primary datum. This can also be datum C if it is listed first. The last datum listed is always the tertiary datum. This could also be datum A if it is listed last. Let us now take a closer look at what the datums actually mean and how they clearly define the position of the tolerance zone. Since the bottom side of the part represents the primary datum, this surface must first be aligned on a perfectly flat support surface, which is the datum simulator A. For this purpose, the part is placed with its bottom side on an inspection plate. Now the part must be aligned on 2 additional datum simulators in order to fully fix it in space. These are 2 further flat surfaces, both perpendicular to each other and perpendicular to the base plate. The reference surfaces A, B, and C thus form a perfectly flat and right-angled datum system for our part. If our part were also ideally shaped, meaning all sides were perfectly flat and perpendicular to each other, then it would make no difference whether we first align the part on datum simulator B and then on C, or first on C and then on B. However, since in reality we do not have an ideally shaped part, the order of alignment does indeed make a difference. To illustrate this, consider the exaggerated real shape of the part shown, which is uneven and skewed. Since, in our case, the left side surface of the part is the secondary datum surface, this surface must be aligned next. We therefore slide the part with this datum surface B onto the corresponding datum simulator B so that it no longer wobbles and is firmly fixed on this reference surface by at least 2 points of contact. Now the part can only be moved forwards and backwards. This movement is finally restricted by datum C by bringing the rear side of the part against the corresponding datum simulator C, which touches the part at least one point. The position of the part is now clearly defined within our datum system consisting of the three reference surfaces. The basic dimensions shown in the drawing, that is, the theoretically exact dimensions of the position of the whole center line or the axis of the tolerance cylinder, refer precisely to this datum system. This means that the specified basic dimension of 114 mm is to be measured from datum simulator B. Accordingly, datum simulator C serves as the reference surface for the basic dimension of 68 mm. The position of the ideal whole center line, or the axis of the tolerance cylinder within which the actual whole center line must lie, is now clearly defined. At this point, it also becomes clear why the order of datums in the feature control frame is of central importance for determining the position. Because the part does not have ideal geometry, its orientation within our datum system varies depending on the order of the datums. For example, in the following we swap the order of datums B and C in the feature control frame. The secondary datum is now datum surface C, and the tertiary datum is datum surface B. After placing the part again on the primary datum A in the first step, we must now align the part in the second step not on datum simulator B, but on datum simulator C. The part therefore no longer contacts datum surface C at just one point as in the previous case, but is aligned so that the rear side of the part rests firmly without wobbling on datum simulator C at least 2 points. Since datum B is used as the tertiary datum, we shift the part in the last step against datum simulator B, which this time touches the part at only 1 point and fully constrains its position. Although the position of the ideal whole center line within our ideal datum system remains unchanged, the part now has a different orientation relative to this datum system. Therefore, the position of the center line relative to the part is different. This also applies correspondingly to the axis of the tolerance cylinder. We can thus see how important the definition and consideration of the order in which the datums are specified in the feature control frame is. We can apply position tolerancing not only to center points or center lines but also to surfaces. To illustrate this, consider the example of a swash plate shown. In the following, we want to tolerate the position of the blue-marked surface, which is inclined at an angle of 110 degrees to the center line and whose center point is 36 mm away from the right shaft shoulder. For this purpose, we first use the tolerance characteristic of angularity. The angle of 110 degrees must not be specified as a dimension subject to tolerance in this case, but rather as a theoretically exact dimension, that is, as a basic dimension. For this purpose, we place it accordingly within a rectangular box. As the reference for the angle, we use the center line as a derived geometry element of the diameter and therefore place the datum triangle directly in line with the dimension line. We have now clearly defined the tolerance zone within which the tolerated surface must lie. It is a rectangular tolerance zone determined by two parallel planes spaced 0.08 mm apart, within which the actual geometry must be located. With the help of angularity, the orientation of the surface is now clearly defined, but not its location. This is because the characteristic of angularity is ultimately only an orientation tolerance, not a location tolerance. In theory, the tolerance zone for the geometric characteristic of angularity may still be shifted arbitrarily, as long as the planes continue to run at an angle of 110 degrees to datum axis B. To restrict not only the orientation but also the location of the surface, we therefore use the position tolerance characteristic. This now also limits the location where the tolerance zone must be situated. The median plane of the tolerance zone must be located at the theoretically exact position, which is 36 mm away from the edge of the right shaft shoulder. By tolerancing the position, the form of the geometric feature is indirectly controlled as well. The two planar surfaces that define the tolerance zone directly determine the flatness of the tolerated surface. The unevenness of the tolerated surface cannot exceed the tolerance value of the position. Similarly, in the previous example, the straightness of the tolerated centerline is directly determined by the position tolerance. Since the centerline must lie within a tolerance cylinder, its straightness must not deviate more than the tolerance value of the position. Let us now take a closer look at the tolerancing of coaxiality and the special case of concentricity. Coaxiality or concentricity may only be applied to derived geometry elements, that is, in particular to centerlines or center points. Let us consider the illustrated example of a shaft. The shaft shoulders at the ends are intended to serve as bearing seats for rolling bearings. A pulley is mounted on the middle shaft section. Thus, the shaft essentially consists of three geometric sections, which are shown here in different colors. These sections must be regarded as independent geometry elements that may deviate more or less from the ideal shape of the technical drawing both in form and in their position relative to each other. To ensure in this case that the center line of the shaft section where the pulley will be mounted aligns with the center lines of the shaft ends, the characteristic of coaxiality is used. Ideally, this means that there is a perfectly straight continuous center line, that is, all geometric elements share a common axis. The characteristic of coaxiality is symbolized in the feature control frame by two concentric circles. The leader line, ending with an arrow, extends along the dimension line of the diameter and thus tolerances the center line of the middle shaft section as a derived geometry element. Now it must be specified to which other center lines the tolerated axis should be coaxial. For this purpose, we again use the corresponding datums. In our case, we use datum A for the center line of the left shaft end and datum B for the right shaft end. Since we also use the center line as a derived geometry element for the datums here, we place the datums directly in line with the corresponding dimension lines of the diameters. In the present case, however, the datums are not independent as in the previously considered cases, where their positioning in the feature control frame requires adherence to the sequence of part orientation. For coaxiality, the part is not first aligned to datum A and then to datum B. Instead, the datums are equal and together form a common datum. Therefore, this common datum is written in a single box in the feature control frame, and the datum letters are separated by a dash. To establish the theoretically perfect position of the common center line, the part is now clamped into ideally aligned bearings referenced to the respective shaft ends. These form the ideal centerline AB. The tolerated axis of the middle shaft section must now lie within a tolerance cylinder whose diameter corresponds to the specified tolerance value of 0.1 mm and is symmetrically or coaxially aligned with the reference centerline AB. It can be seen that in this case as well, the location tolerance of coaxiality again includes the form tolerance of straightness. The centerline cannot be more curved than the tolerance value of the coaxiality. The feature of coaxiality can, in principle, also be applied to the centerline of a hole. The example shows a round metal disc with a diameter of 40 mm and a hole with a diameter of 25 mm. Again, it is important to note that we are ultimately dealing with two different geometric elements, each having its own independent centerline, which in practice are not coaxial. With the feature of coaxiality, we can now ensure that the centerline of the hole runs coaxially within a defined tolerance zone relative to the centerline of the metal disc. In principle, it is extremely difficult to determine the centerlines of such thin metal sheets using measurement techniques, as they are extremely short and therefore practically non-existent. In such cases, it is not the centerlines but the center points that are toleranced. In this context, we no longer refer to coaxiality, which applies to the centerlines of cylinders, but to concentricity, which refers to the center points of circles. However, the principle for establishing the tolerance zone remains the same. For this reason, concentricity uses the same symbol as coaxiality in the feature control frame, two concentric circles. Since the reference point for the toleranced hole center is also a point, namely, the center of the circular metal sheet, a single datum A is sufficient here to fully define the location of the tolerance zone. The center of our hole must now lie within a circular tolerance zone with a diameter corresponding to the given tolerance value of 0.1 mm, whose center point coincides exactly with the center of the circular metal sheet. In the following, the part is no longer considered as a flat ring with a small height, but as an extended tube with a corresponding length. Here, too, we have two geometric elements, an outer cylinder describing the outer surface of the tube, and an inner cylinder describing the bore. The characteristic of coaxiality in this case results in a tolerance cylinder with a diameter of 0.1 mm. The axis of this tolerance cylinder corresponds to datum axis A, which is derived from the ideal position of the centerline of the tube. The centerline of the actual bore must now lie within this tolerance cylinder. However, we could also use concentricity here to define the position of the bore. The interpretation would be somewhat different in this case. Concentricity would apply to each cross-section individually. Each cross-section essentially forms a new center point as a reference. This reference point is determined by the outer contour of the tube in the considered cross-section. Around this reference point, a circular tolerance zone with a diameter of 0.1 mm is defined. The actual center point of the bore must then lie within this zone. However, Since a new center point is defined for each cross-section, the centers of the tolerance zones along the tube no longer lie on a straight line as they do in the cylindrical tolerance zone. Because concentricity uses the same symbol as coaxiality, it must be explicitly stated when concentricity, rather than coaxiality, is intended as the characteristic. Without any further indication in the feature control frame, coaxiality along the entire axis with a typical cylindrical tolerance zone would apply by default in this case. If, however, concentricity in every cross-section is intended, the letter combination ACS is placed above the tolerance frame. This stands for the initial letters of the words any cross-section. Now let us move on to another location tolerance, symmetry. Consider the illustrated example of a shaft with a keyway cut into it. In this case, it must be ensured that the keyway is as symmetrical as possible to the shaft. Here again, we are dealing with two different geometric elements. On the one hand, the circular shape of the shaft, and on the other hand, the rectangular keyway for the key. Both geometric elements have their own median planes and differ from each other in practice. The symmetry characteristic now defines a rectangular or cuboid-shaped tolerance zone within which the median planes must lie. The symbol for symmetry consists of three horizontal lines, with the middle one being somewhat longer. Since in our case the median plane of the keyway is being tolerated as a derived geometric element, the leader line of the feature control frame is again placed in direct extension of the dimension line for the keyway width. Next, in the second box of the tolerance indicator, the width of the tolerance zone is specified again, in our case 0.05 millimeters. Now, a datum must be given indicating to which geometric element the keyway should be symmetrical. In our case, it should be symmetrical to the median plane of the shaft. Since this is again a derived geometric element, the datum triangle is placed in direct extension of the dimension line for the shaft diameter. The tolerance indication is now to be interpreted as follows. The median plane of the keyway must lie within a tolerance zone defined by two parallel planes spaced 0.05 millimeters apart. This tolerance zone is symmetrically arranged relative to the median plane of the shaft as datum A. Next, we address the question of how to determine the median plane of the keyway in practice to check whether it lies within the tolerance zone. To do this, the distance from one side of the keyway to the other is measured at a sufficient number of points, and then the respective midpoint is determined. The collection of these midpoints now forms the median plane. This median plane must lie entirely within two parallel planes symmetrically arranged relative to the median plane of the shaft. Next, the runout tolerances, which control circular runout and axial runout, will be examined in more detail. Let us first take a closer look at the tolerance of circular runout. For this purpose, we consider the illustrated part with a tapered shaft section. To ensure that the tapered surface does not wobble but runs roundly during the rotation of the shaft, we apply circular runout tolerance. The symbol for this radial runout is an arrow pointing diagonally upward. Following this is a tolerance value that defines a ring-shaped tolerance zone with the corresponding width. During the rotation of the shaft around the datum axis, for example, the measuring tip of a dial gauge must always remain within this ring-shaped tolerance zone. Let us take a step back here. It is important to note that we are dealing with different geometric elements, each having its own centerline and generally being oriented differently relative to one another. Accordingly, it also makes a difference whether we align the shaft for rotation on the bearing surfaces marked in red or on those marked in green. Depending on this, we obtain a different datum axis for the rotation, and the dial indicator readings will produce different results. Therefore, a datum must again be specified to clearly define the alignment of the part for rotation and the resulting runout. In the present case, we choose the larger shaft shoulders, more precisely the centerlines derived from them, as the common reference. The part must then be aligned or clamped on these shaft shoulders during the runout inspection. As already explained, in circular runout the circumference line of a cross-section perpendicular to the datum axis must lie between two concentric circles that are 0.05 millimeters apart, with their centers located on the datum axis. Note that the size of the individual tolerance circles does not matter, as long as they maintain a distance of 0.05 millimeters from each other and their centers lie on the reference axis. This must be the case because circular runout applies basically to every cross-section along the tolerated surface. Therefore, the tolerance zone diameter inevitably becomes smaller if the runout inspection is performed further to the right. The width of the tolerance zone of 0.05 millimeters, however, remains constant at all times. It is important to note that during circular runout inspection, measurements must be carried out independently at different cross-sections along the tolerated geometric element. The dial indicator is reset to 0 before each cross-section measurement, and the measuring process begins anew. At first glance, runout may seem identical to the form tolerance of roundness, whose tolerance zone is also defined by two concentric circles. However, the crucial difference is that in runout the position of the circles is clearly defined. While in roundness the position of the tolerance zone center is freely selectable, in runout it is always located on the datum axis. This ensures that when the shaft rotates around the reference axis, not only does the circumference line not deviate excessively from the circular path, but it also does not wobble too much. For example, if the conical shaft section were manufactured too eccentrically due to production errors, this would immediately be detected during the runout inspection and lead to rejection accordingly. If, on the other hand, we had only tolerated roundness, the tolerance ring could be shifted so far that the circumference line might lie completely within the tolerance zone. The part would then be considered acceptable. Runout is therefore a stricter criterion than roundness but includes it, thus imposing higher demands on the manufacturing process because the position of the tolerance zone is additionally restricted and must be complied with accordingly. Fundamentally, runout not only includes roundness but also concentricity, as the centers of the cross-sections must not deviate too much from the ideal position. Otherwise, the circumference line will inevitably lie outside the tolerance zone. The circular runout just explained is primarily used for rotationally symmetric but non-cylindrical surfaces. For cylindrical surfaces, however, it is usually not suitable. To illustrate this, let us now consider the conical shaft section as cylindrical and continue to tolerate it with circular runout. Since in this case each cross-section is checked separately for circular runout, this type of runout tolerance cannot prevent the part from having an unintended conical shape. Each cross-section meets the circular runout requirement in this case, and the shaft is considered acceptable, even though the surface is obviously not cylindrical. Even if the shape of the shaft were strongly concave, the circular runout could still be fulfilled for each cross-section, although the shape deviates significantly from the actually desired cylindrical form. To also tolerate this cylindrical form, the so-called total circular runout is used in these cases. This total circular runout is symbolized in the tolerance indicator by two diagonal arrows connected by a horizontal line. In total circular runout, the tolerance zone is a hollow cylinder that is coaxial with the datum axis AB. In this case, the cross-sections are not checked separately but the shaft as a whole. That means the dial gauge is zeroed only once at the beginning of the measurement, and then the entire surface of the shaft is checked to ensure that no value lies outside the tolerance cylinder. At first glance, total circular runout also appears identical to the form tolerance of cylindricity, whose tolerance zone is likewise defined by two coaxial cylinders. However, the crucial difference here is that for total runout the position of the cylinders is clearly defined. While in cylindricity the position of the tolerance axis can be chosen freely, in total runout it always lies on the datum axis. This ensures that when the shaft rotates around the reference axis, the surface does not only deviate excessively from the cylindrical form but also does not wobble too much. Total circular runout therefore includes, analogous to circular runout, not only cylindricity but also coaxiality. The center line of the tolerated cylindrical surface must not deviate too much from the datum axis, otherwise the surface will wobble during rotation and no longer remain within the tolerance zone. With runout, we can ensure not only that a surface does not wobble too much in the radial direction, but also that a surface does not tilt excessively in the axial direction. This is then referred to as axial runout. Here again, a distinction is made between axial runout and total axial runout. Let us first take a closer look at axial runout using the example shown. The tolerance symbol is basically the same as for circular runout. However, the tolerated surface is not aligned radially to the datum axis but axially. Accordingly, the arrow of the feature control frame for axial runout points in the axial direction. In this axial direction, the deviations during the rotation of the shaft are recorded. The shaft is aligned using the datum A, which in this case corresponds to the centerline of the respective shaft shoulder. During the measurement of axial runout, the part is aligned using this shaft shoulder at a bearing. A dial gauge is then placed on the surface to be inspected. As the shaft rotates, the dial gauge measures the axial deviations and thus records any wobbling of the surface. Note that the recorded curve lies on a perfectly cylindrical surface, so the deviations are measured only in the axial direction. These measured deviations must now lie within two circles spaced apart by the tolerance value, which in our case is 0.05 millimeters. For axial runout, this cylindrical tolerance surface must be maintained independently at every other diameter value. To do this, the dial gauge is placed at a new location on the tolerated surface and the inspection process is repeated. Regardless of the axial position of the tolerance circles from before, the measured deviations must again lie within two circles spaced 0.05 millimeters apart. The tolerance circles are realigned in this way for each measurement. This procedure must be repeated at different locations on the tolerated surface in order to gradually cover the entire surface as comprehensively as possible. Since the tolerance zone is essentially redefined with each measurement, axial runout is particularly suitable for non-flat surfaces, such as a convex shape. However, this example also shows that if a surface is supposed to be as flat as possible, axial runout is not suitable. In this case, for example, axial runout would be met at all measured diameters and the part would be considered acceptable, even though such a convex shape is undesirable and the surface should be as flat as possible. In this case, it makes sense to inspect the entire planar surface in a single operation. The inspection diameter is continuously reduced during the rotation. In this way, a height profile of the entire surface is created. The tolerance zone is now formed by two circular surfaces whose distance corresponds to the tolerance value of 0.05 millimeters. The recorded axial deviation profile must lie entirely within this cylindrical tolerance zone. Total axial runout also implicitly includes perpendicularity as an additional positional tolerance, because the entire surface must not deviate too much from perpendicularity relative to the datum axis. Otherwise, the surface wobble would be too great, and the axial runout would no longer be maintained. Thus, total axial runout also implicitly controls the flatness of the surface. Finally, an important auxiliary indicator for the positional tolerances will be examined. In the video on form tolerances, we have already explained three of these auxiliary indicators in detail. These were the direction element indicator, the section plane indicator, and the collection plane indicator. In the case of positional tolerances, the orientation plane indicator plays an important role. It is always used, for example, when a centerline is tolerated between two parallel planes to clearly define the orientation of these planes. Let us consider the illustrated part with two holes. The centerline of the upper, blue-marked hole should run as parallel as possible to the centerline of the lower hole in the sectional plane of the side view. The illustration shows a possible path of the centerline of the actual hole, which is not parallel to the centerline of the lower hole. Therefore, the centerline of the upper hole is toleranced with parallelism, using the centerline of the lower hole as datum A. The tolerance centerline must now lie between two parallel planes spaced 0.05 millimeters apart. However, at this point, it is not clearly defined which datum these planes refer to and, above all, how they must be oriented. Here too, it must be noted that the part in reality deviates from the ideal geometry shown in the drawing. The key question now is whether the tolerance planes, for example, must be aligned parallel to the top surface of the part or to the bottom surface. And how are we supposed to know at all whether the planes should be aligned parallel rather than perpendicular? Thus, we see that the orientation of the parallel tolerance planes is not defined at all. This is precisely where the orientation plane indicator comes into play. It clearly defines the orientation of the planes. In our case, the planes must be aligned parallel to the bottom surface of the part, which is referenced as datum B. To also control the position of the centerline in section AA of the top view, we could add another feature control frame directly below the first one. In this case, the tolerance zone is additionally limited by two parallel planes spaced 0.08 millimeters apart, which are now oriented perpendicular to datum B. The resulting overall tolerance zone is a rectangular box with a height of 0.05 millimeters and a width of 0.08 millimeters.